Good morning. My name is Beth Capellas, and I am the Sales and Support Manager here at Triangle Microworks. Welcome to our latest webinar series, IEC 62850, Substation Design and Testing. This is a two-part series, and today's webinar is part 2, Test Your Design, Simulating and Validating an IEC 62850 Substation Design. Part 1, which was titled IEC 62850 Substation Design Workshop, was previously held on August 10th. You can go to our website to view this webinar at any time. It's okay if you haven't watched part 1 to participate in today's webinar. They are related, but the material does stand on its own. The webinar is scheduled to be 1 hour long. We have a lot of material to cover today, but we will try to get to answer questions. The audience is on mute, so please submit your questions online using the webinar toolbar under the section titled Questions. You can submit questions as soon as you have them. Please don't feel you have to wait to the end. We will begin answering questions online as we have several engineers monitoring the questions and responding to them directly. We are also happy to stay on after the webinar is over and answer as many questions as we can. So with that, I'd like to introduce the folks that are behind the scenes today answering those questions. Today we have with us Matt Green. He's a senior application engineer here at Triangle Microworks. And we also have Dave Buchenauer, senior developer for DTM, also at Triangle Microworks. Next, I'd like to introduce our speakers. We have Christoph Brunner with us today. Christoph is president of IT for Power. He's also a well-known utility industry professional and 62850 expert with over 30 years of industry experience. Christoph has been involved in the development of the standard since the beginning. He is convener of Working Group 10 and member of Working Group 17, 18, and 19 of IEC TC 57. He is an IEEE fellow and a member of several IEEE working groups, as well as a member of the PSRC main committee in the subcommittee H. Next, we have Jackson Moore, application engineer here at Triangle Microworks. Jackson received Bachelor of Science degrees in both electrical engineering and computer engineering from North Carolina State University and has a background in power systems engineering. Prior to joining Triangle Microworks, Jackson spent 5 years as a microgrid system engineer, where he designed and developed load management control systems for multi-source microgrids. In his current role of application engineer, Jackson serves as a bridge between our customers and our development team, seeking to understand and solve the unique, complex challenges our clients face. So now that you know everyone, I'd like to just go over a little bit of background of Triangle Microworks. We were established in 1994 and have over 28 years of communication protocol experience. We are headquartered in Raleigh, North Carolina, and have customers in over 70 countries. We work mostly with equipment manufacturers, electric utilities, and system integrators. The products we offer all support the standard SCADA protocols and fall into 3 categories. First category is source code libraries. We license source code directly to manufacturers for use in their devices and systems. This allows for a much faster time to market and greatly reduces their costs and development time. Licensing a source code library also includes support for your implementation and any issues that may arise in the field. We also provide testing tools supporting these libraries and protocols. These tools are used for communication testing in the lab or the field. They are designed to troubleshoot, simulate, and automate testing for both a single device or a complete substation. Lastly, we also provide a SCADA data gateway supported on both Linux and Windows for protocol translation and data concentration with standard SCADA protocols as well as OPC. It is available as software only or pre-installed on hardware. We are heavily involved in the standard committees that support SCADA protocols like UCA Group for 62850 and DMP user and technical committees. Through our participation, we help define the protocols, stay up to date on the changes taking place, and ultimately provide feedback based on our customers' needs as the protocols continue to evolve. So now that you know a little bit more about Triangle, I'd like to go ahead and hand it over to Christoph, who will kick off the webinar. Christoph, I'll go ahead and make you a presenter.
Thanks, Beth, and welcome everybody as well from my side. I will share my screen. Okay, you should see my screen now. I hope you can hear me well. So in the first part of this webinar series, Jackson had demonstrated how the design of a digital substation can be made using 61850 System Configuration Language, or SCL. In the second part, we will now show you how you can verify that the design works before you even need to configure the devices. With IEC 61850 and the SCL, the System Configuration Language, we have basic information that describes the system functionality in a machine processable format available. So let's have a look at that. So we will first discuss what can be done with a design for a digital substation by using IEC 61850 and the IEC 61850 SCL. In the second part, we will discuss why that is possible, what are the features in the standards that support that, and then finally, we will introduce the tool that we have that supports this simulation, which later will be demonstrated by Jackson in the second part of the webinar. So now let's have a look. In the substation protection and control system, traditionally, we have relays that are wired together, that are wired to the process. Signals are exchanged over these wires as binary or analog information, and that's basically what realizes the applications in a classical design. When we now move to a digital substation, things have changed a little bit. A digital substation is typically characterized through the fact that our devices or relays are now intelligent electronic devices, microprocessor based, that have communication capabilities. The information exchange between the devices is now done through communication. And another characteristic of the digital substation is that we integrate merging unit, switchgear interfaces to bring communication down to the process. So that's more or less the key characteristics of a digital substation. Now, how does this influence the way how we can look at the applications that we realize in our substation protection and control system? An application is typically realized through various functional elements, like distance protection elements, and these functional elements exchange signal between them. In IEC 61850, those functional elements are characterized as logical nodes. So we see here 3 logical nodes for 3 different distance protection zone elements. We see a trip logic. So the application that we have illustrated here is a breaker failure application. So the trip logic will decide if a trip shall happen. The trip would go through the breaker interface and as a wire into the breaker. In the same time, the trip signal that is sent to the breaker is also initiating our breaker failure function. The breaker failure function will supervise if the breaker has opened, if the breaker failed, maybe doing a local retrip, and if it still fails, we'll do what is called in 61850 external operate, data object opx, that is basically going to the neighbor breakers that we need to trip in order to clear the fault. So what we see for these little applications, we have a bunch of functional elements, 61850 logical nodes, and we have signal flow between these elements. The next slide shows another look at the concept of an application, focusing now a little bit on the logical nodes that are representing the functional elements that work together. So a logical node has outputs that are our data objects in the 61850 world that are standardized. We may have parameters that influence the behavior. An example would be an operate delay for a protection element. We also may have controls. A control could be to enable or disable a protection element, or it could also be a control to request an opening or a closing of a breaker when we do a controlled breaker operation. But then we also have inputs that are typically signals coming from other logical nodes, and the inputs and outputs together flow between these logical nodes to implement the application as we have seen before. Some logical nodes are interfacing process equipment, like the logic node XCBR that we have seen, which interfaces to the circuit breaker. So the equipment in that case would be the circuit breaker. So in these cases, we also have the logical nodes are associated to physical inputs and outputs of the system. Information exchange between the logical nodes, if that's within the device, that's typically done through software. If it's in different devices, then it will use Goose messaging, one of the communication services of IEC 61850. So basically, we are getting now to our key topic, the function simulation. As in a digital substation, everything is digital. We can as well simulate things in software. As you have seen, the key aspects of an application, which are the functional elements and the signal flow, those are both described in the system configuration language in a machine processable way, which basically allows us that a piece of software can use that information and simulate the behavior of the system. So basically, we can create a digital twin of the system, or like Jackson would say, maybe a digital cousin, as it may not be exactly one-to-one the same behavior. Why would we want to do that? I think the first obvious use case is that we want to test the design in an early stage before implementing it in the devices. But there is more that we can do, and that's what we'll discuss today. But there is more that we can do with a functional simulation. Another example is a unit testing of a device. Let's take the use case that you have a device in your live system that has failed. You need to replace it. So you get a replacement ID, you have to configure it, and you want to be sure that the configuration is really working as expected, that you configured it right. So before you put it in the real system, you can put it in a test bed where the remaining devices are functionally simulated and interacting with the physical device that you want to verify the communication. Other use cases may verifying test scenarios that you need to test in a live substation, the whole virtual isolation concept that IEC 61850 has. So you can on one side test these scenarios using functional simulation, but another opportunity is as well, as this involves a certain sequence that maintenance staff needs to do, you can also use the simulated environment to train maintenance staff. So we can also use simulated environment for trainings, operator training, maybe another thing. So when you want to train an operator on your SCADA system, you can simulate the complete behavior using functional simulation, and the operator can be trained on the SCADA system. So that's some of the use cases for the functional simulation. Okay, now that we understood what can be done in a digital substation design, let's have a look of what features in IEC 61850 support that. The key element here is the SCL, or System Configuration Language file, that I hope you are partly familiar. I mean, Jackson showed in the first part of the webinar how such a file was created. So basically, it's a XML-based documentation of relevant configuration aspects, and it's structured in different sections where all the sections have a dedicated purpose. The substation section, that's where we have the key information for our functional simulation that basically describes the topology of the substation, functional requirements, the structure of the substation. Then in the IED, we have an ID section for each of the IDs that we use in our system, and it basically describes the data model of the ID as well as the communication configuration, like goose, report, and sample value messages, how those are configured. Last, we also have the communication section. That's where we include all the information related to the communication network. So basically addressing information for our system. Now, how does this look? So with regard to the functionality, we have in our SCL substation section, the hierarchical structure. It starts with substation, voltage level, then we have the bay, and then we have our conducting equipment. Conducting equipment can be a circuit breaker, a disconnecting switch, and we can also associate to conducting equipment logical nodes that we specify for the functionality. Like associated to a circuit breaker equipment, we would have a logical node of the class XCBR associated. In the substation section, we can as well describe functions, hierarchically structured functions, like an overcurrent function with the sub-functions and logical nodes associated, like the overcurrent element, the measurement, the current transformers, where we get the signals from. In this case, they are also grouped here under the overcurrent function. This whole structuring of function is completely user-defined. When you do the specification, like Jackson had demonstrated last time, that's when you basically did build up this structure. So we have another function here for the trip, and we have a function breaker failure, where we find our logical node breaker failure. So this is all described in SCL. When we realize a system, we start with the specification and then we implement it, which means we associate our specified functionality to IDs. And again, this is implemented and documented in the system configuration language file. We see here an extract where we have in the function breaker failure specified logical node RBRF to be used. And then what we see here, we see the reference to the ID, which is implementing that particular function that we have specified here. So with that, we can associate our specified functionality with the realization within the devices. So that's about the function and the functional elements. Next is the signal flow. Signal flow can be described as well in SCL, and basically already with the part 6 that we have today, it is possible to document signal flow based on goose messages, mainly by external references. So basically, we can have here, we have a logical node, the breaker failure that is realized in an ID. And what we see here is the input to these logical nodes documented through an XREF that points to the signal, which is the trip signal from a logical node PTRC that is used as an input to this breaker failure function. It's the breaker failure initiate input that we have seen before. So that can be documented through an XREF. We can also indicate what service we will use, and we could also indicate where the control block is associated to that goose message. Another element that I would like to point out here, so we not only have the status value, which is the general attribute here as an input, we also configure the quality to be an input, because it's a good practice to always associate as well the quality, use the quality in your signal flow and use the quality in your application. So that's the way how external references can document signal flow between the devices that is realized with 6150 communication. But as we have seen earlier, multiple function elements can be realized within the same device, and then we have an internal signal flow, and we would also like to document this. And for that, we are currently working on an extension to the standard, which is the 61850-90-30 technical report. It's a draft that defines various extensions. Associated to that is a namespace IC 61850-6-100 The reason that this number is not identical is that within this namespace, we include as well formally other extensions that are defined in other parts of the standard. So the key element now for our topic today that we add there is an element source ref, which can be used to document signal flow between logical nodes from our specification, so from our substation section, signal flow independent of allocating functions to IDs, independent of a communication mechanisms. So this allows us basically to document the complete application as we see it. We have our logical nodes in the specification, in the substation section, and with the source refs, we can document these internal signal flows, or these signals flow in general from a specification perspective. When we now realize the application, then we have to associate IDs. And what we now see is that signals that have before been flowing between IDs are now going on virtual outputs and virtual inputs and are carried over with a goose message. These signals are still internal. The blue ones have now been translated into a goose message. All the signals are documented with the source ref in the substation section. The blue ones that are between the devices are documented with a next ref in the ID section associated in the specific ID that implements this logical node. And again, in SCL, we can document how our specified input is realized with the real reference. So we can specify our input reference, but then we can also specify how this is realized with an xref through an xref address. So here we see the xref address that points to where this specified input is realized. Also in SCL, we can document, once we have realized the interaction with goose, we can document how the goose publisher, how the message is constructed, what is the control block, what is the data set, and the subscriber that receives the signal through our xrefs. So that means when we implement an application in IEC 61850, we first have to specify the details of the application with the signals that we want to exchange between our functional elements. This is similar to a wire diagram in a conventional design. We then have to allocate the functions to devices, to IDs, and then based on this allocation and the complete signal flow, we have to translate the external signals here into goose messages and associated data sets. And that's basically, when we have all that together, that will create all the information in our SCL file that we then can use to design our system, to configure our system, but also to simulate. So now that we have understood the elements that support the function simulation, let's have a quick look at our tool that is supporting this before Jackson will then demonstrate that tool. So the tool we are talking about is our distributed test manager. It's a tool that can simulate SCADA communications in the substation, perform automated tests to confirm system or individual device behavior. It supports multiple protocols. It's script. It includes a script and action-based test manager. It has a 650 goose and report viewer, and the focus for our discussion today, it supports a script-based simulation of a system that is described in SCL in the system configuration language. Just about the protocols we support. So we support IEC 61850 with all the services, MMS, goose, sampled values, but also secure and routable goose and sampled values, where the key distribution center from Garibaldi gets involved. We also support the other SCADA protocols like DMP, Modbus, 101, 104, and TARZ2 or ICCP in the control center communication protocol. But the focus today is our behavior simulation. So we have one feature of DTM is that it supports behavior simulation. The behavior can be described either in JavaScript or in 61131 structured text or function block diagrams. We have mechanisms built in to debug, to test, to run the stuff. We can watch variables live as the simulation is executed, so we can also have a look at the internal variables. When it now comes to our functional simulation, so the application is now a digital substation. That's what we have seen earlier. Our application is decomposed into logical nodes, which are functional elements which exchange data, and they may have signal exchange to equipment. So at the same level, that's also how our functional simulation works. So we have elements in our functional simulation that simulate individual logical node behaviors, but we also have elements that simulate conducting equipment, like a breaker or a switch. So simulates the opening, provides the feedback to the logical nodes that interfaces with it. In order to perform this simulation, we need some additional control. One of them is a control through a user interface. If you want to run a test, you may want to simulate a test case where the breaker opens, or a test case where the breaker fails, so that you can verify your breaker failure function. So through a user interface, we can influence our functional simulation in DTM. Also, of course, we need to consider the behavior of the process, the topology. When a fault has been cleared, the current stops flowing, so the simulation of the protection element that discovered or that determined the operate signal needs to know that it has to set that back to false because the fault has been cleared. So there is also some additional information going into the function simulation for the different logical nodes. So to summarize, DTM basically includes a library with a default functional behavior of more or less every major logical node, as well as major conducting equipment. Here illustrated is the simulation of the XCBR, the behavior that we have in our XCBR logical node simulation. The behavior can be customized, so we have a default behavior available. You can customize that using either JavaScript or 61131. And with that, I think it's time to hand over to Jackson, that will now demonstrate what I have tried to explain here based on the design that he created in the first part of the webinar a few weeks ago.
Great, thanks, Christoph. We are going to just pause for just one or two questions real quick, if that works. So Christoph, this question is for you. It's a question with a comment as well. What standard is used for IED name, and do you only have 6 characters for the name? I thought that IEC 81346 is recommended.
Okay, I was muted, sorry. Okay, so, well, for the 6150 perspective, there is no requirement how you create your ID name. The ID name can be completely configured in SCL. So it's a configuration element that we have to design to use to determine when we build the system. Yes, there is a recommendation on this standard that you mentioned that could be used, but it's not mandated to use that. About the names, I think there is more than 6 characters allowed. There is somewhere in the standard the limitations are defined, but the limitation is such that the total of your logical device name, which is created by the ID name, the logical device instance, this should not be more than 64 characters. So I think the ID name can be way bigger. than 6 characters. Did that answer the question?
Yes. The next question, does your simulation have HMI of the breakers and other objects?
Yes.
I can take that one, yes. And we're going to get to see that in action here in just a moment.
Okay, sorry, I think we did double speak.
Okay, well, perfect. With that, let's go ahead and segue over to Jackson. I'm going to make you the presenter. Okay, Jackson, you should have the screen.
All right. All right. Thank you, Beth, as well as Christoph. Thank you, Christoph, for kind of explaining the what and the why, as well as some of the how of what we're accomplishing today. And that is, simulating our SCD and all the reasons that we're capable of doing that. So before I get into the demonstration, I do just want to provide a quick explanation of the tool that I'm using. So Christoph gave us a brief introduction, but I'll show you a little bit more here. So what you see up on my screen now is DTM, or Distributed Test Manager. It is fundamentally a multi-protocol test and simulation tool. So it does include support for DNP3, 101, 104, Modbus, TASI2, but today I'll be using 61850. And it is capable of simulating both servers and clients in all of those different protocols. Particularly for client functionality, today I will actually be using another one of our tools, TestSuite Pro, you might be familiar with from past webinars or from using it yourself, hopefully. But I'll go ahead and save the introduction of that until the end when we actually pull that up. So aside from just communications, DTM is also capable of simulating device behavior. So that will include JavaScript that we'll take a look at here in a little bit, as well as IEC 61131, structured text and function block diagrams. And then finally, we have the Substation Simulator, another tool that's built into DTM. And that's what I've used to build the layout that you see on my screen now, which includes the one line, the substation section, and our IEDs. And what I'll be doing today is walking through how I created this simulation and what I can do with it now that I have it. So the first step is to actually use the Substation Simulation Import Wizard. So to do that, I just came up here to File and imported my wizard. I selected my SCD file and I hit OK. That brings up this screen here. And this is what you would need to do should you have an SCD of yourself. And I'll briefly walk through a couple of these options, but most of them will make more sense once we've actually completed the demo. So for example, functional nodes, this will be the scripting elements that allow our system to actually function and have behavior. Generate single line diagram, you can get a little bit of a peek of what that looks like here behind the window that I have up now. Generate XY coordinates from the SCD file. So there is the ability within 61850 to specify XY coordinates. So where on a screen, for example, an HMI, will a specific piece of conducting equipment live? So that would tell us where a specific breaker is going to be in space in relation to other conducting equipment that it is connected to. Today, I won't be using the power simulation, but you can use that to simulate voltages and currents flowing through your system, just to give it an extra element of realism. And then finally, generate simulation controls. That will allow me to automatically trigger protection elements over here on the right, and we'll get to see that in action here in a little bit. But once I select my SCD and bring that in, I'm able to do all of this. To use an analogy, I think of an SCD as kind of like a blueprint for a car, where the frame of the car captured in the blueprint would tell us the different pieces of conducting equipment, where they are within my system, and what they're connected to. You might think of the logical nodes as the different components of the car that perform functions, like the different brakes, engine, transmission, so on and so forth, and those will exist down on the different IEDs that we have down here at the bottom. And then finally, our signal exchange. That's also documented in my SCD. And that might, in a car analogy, you could think of the wiring that connects different components to each other, or maybe fuel lines or different hoses. So once we have all that information contained in an SCD, just like if you had the blueprint for a car, you could build a pretty good approximation of that car. We're also able to build a realistic simulation of what our substation should actually do. So Again, we've already talked a little bit about the single line and how that was generated. You'll notice that it looks pretty similar to the to the single line that we had over in Helix. Just to refresh your memory, or in case you weren't a part of that last webinar, I encourage you to go watch it. It is available on YouTube. I'll go ahead and pull that up now. So I won't be using Helix much today. I really just want to point out that the single line and the layout for the different components, we did set that up and design that in Helix. That information was captured in the SCD. And when I did that import wizard over into DTM, we were able to recreate it. The next thing was that we were able to also bring in all of our different IEDs. And these are visible down here in my IEDs folder. So our SCD contained a data model for each and every IED contained within our system. And you might remember we had 6 different bays visible here on the one line, and each bay over in my SCD has 6 different IEDs contained in it, and those perform different roles. Conveniently, you can tell where the IED exists and what its function is based on its name. That's of course because we named it so over in Helix. So E was the name of our voltage level, which everything exists in. 01 denotes the bay. BCU refers to a bay control unit, where BPU would be a bay protection, backup protection, and process interface unit. And this is the ID that interfaces directly with the physical breaker, opening and closing it. If I wanted to see what the configuration for one of these IEDs looks like, I will point out that this is done automatically once I imported the SCD. But here you can see the IP address of this IED was captured and set. I was able to bind it to a specific network adapter on my PC for publishing Goose messages. If I was using routable Goose, I could specify a separate IP address for that. In this particular case, we won't be using routable Goose or secure and authenticated Goose, but if that is something that you're interested in, we do have a webinar in the past, and we'll likely do another one in the future. Please let us know in the questions if you guys would be interested in more information on that. So aside from just communications, we also have the data model of our IED. So to view that, I'm just going to come in here and show model. So this will be the data model from our BCU. Much of the information contained in this data model really came from the ICD, or IED configuration description, which came from the manufacturer. It defined the capabilities of this IED and gave us a layout for the different logical devices and logical nodes that would be on it. However, once we imported that into Helix and configured it, it also contains other information such as the signal exchange. So these would be the Goose control box and report control box that are contained on my device. Now, again, fundamentally, what DTM is a simulator for industrial communication protocols. So if I was to say, open up one of these Goose control blocks, navigate to a data set on that device, and then navigate to a specific point that was within that data set, I could manually come in here, manipulate this value. In this case, it's an OpX, or an operate external general signal on an RBRF, the breaker failure logical node. If I was to change this, because it is part of a Goose data set, it would publish that message out on the wire, and any IEDs which were subscribed to that particular Goose control block or Goose message would receive that message. Those could be simulated IEDs like I have over here on the left, or even a real physical IED that you might have set up in a lab. But by itself, you know, it's powerful and useful, but it doesn't yet include behavior. I would have to come in here and manually toggle this value in order to elicit a response on another IED. And that's really where our behavior comes in. So as Christoph talked about earlier, the all-important substation section. So the substation section is designed really early on in the engineering process, typically when you're building an SSD, or system specification description. However, that information is all carried over to and even added to once we move into the implementation stage when we're trying to create our SCD, or system configuration description. So all of the conducting equipment contained within that substation section has been represented over here. So again, we see our substation name is Raleigh. E represents our voltage level, just like we saw down here for our different IEDs. And then we can see the different bays that are contained within it. So for example, if I open up bay 1, I can now see the different pieces of conducting equipment that make up this bay, as well as some different functions that are inside of it. You might recall from last time, we talked about how functions are really just collections of L nodes or logical nodes that are all working together to perform some common goal. So, as Christoph alluded to, there's kind of a mirror of each logical node in both the substation section as well as on a particular IED. Now, depending on how your your project has been implemented, you may or may not have the exact same logical node down in your IED section that you have up in your substation section, but that is typically the goal. And then there's the opportunity within the SEL to link those two together. And that's what was done here in our particular SCD that we created using Helix. So if I come in here to one of these specific L nodes from the substation section, and I go ahead and manage IED associations, what's happened automatically is it has been associated with a logical node, and that's because of data that's contained within the SCD. If that wasn't done automatically, then I could come in here and click this association. But effectively what it does is it links the outputs, parameters, and controls of this specific L node with a logical node that exists down on an actual IED. So in this case, this L node from my substation section has been associated with an XCBR that exists on the PIU in Bay 1. So we're getting closer. We've now linked our substation section down to our IEDs, but now it's time to link the communications that are flowing between our different IEDs. So those goose messages, all important goose that replaces wire, signals that go between different IEDs. And we now need to link them up to our functional nodes up here, or LNs up in the substation section. So to do that, or to see how that was done, I'm going to come over here to my input section. So for this XCBR, we've defined a couple different inputs that we think a typical XCBR might have. So those would include a trip signal, for example, and we can see this particular XCBR has been configured to have up to 7 different trip inputs, 5 of which are used. And they are configured to refer to XREFs that point to goose messages that are coming from other devices. So for example, here would be RBRF op external. So this is going to be a breaker failure signal. If a breaker in another bay, in this case, it actually will be bay 2. If that breaker fails, the RBRF, or breaker failure logical node, on that device is going to publish the op-x general signal. Now that is configured as an input into the LLN0 specifically of my bay 1 PIU. So I didn't have to do this mapping manually because the information needed to do this was contained within the SED in really 2 different ways. So first and most importantly, it's contained within the substation section. So that defines sources, source refs, or it contains source refs as part of the 6-100 extension that's currently being worked on within the working group. And it contains what inputs are necessary for a given L node to function. Now, crucially, once we moved into the implementation stage, that source ref included a link to an XREF that actually implemented or realized that signal. In other cases, a source ref might point to a connection that's within a single IED, and that's what we see here. You might notice that this path looks a little bit different for this connection up here at the top than these ones down here at the bottom. These lower ones point to specific points on IEDs down in my IED folder section. This path that you see here is basically a file tree hierarchy that is we refer to as a DTM path that points to a specific point on an IED that we're simulating. Whereas what we see up here, this Raleigh E01 trip PTRC, that actually refers to a point on another functional node or simulated L node that we see over here in the substation section. And that's because this is an internal signal. In this case, this particular manufacturer chose to put 2 PTRCs, one on the protection device, as well as one on the PIU itself. And the PTRC on the PIU is actually receiving that trip signal and then forwarding it on as sort of a proxy over to my XCBR. Finally, these different, I guess, pieces of data that exist on this within the substation section are linked to my single line, and this is what allows me to actually animate. So for example, if this L node, the XCBR had its position value set to open, this is of course in bay 1, then this breaker down here would also reflect open. I know this is a lot, but I do have to really, I hope you guys can get excited here, because there is one last piece that's not necessarily contained within the SED itself, but some of the secret sauce that we contain here in DTM that actually makes this all possible. We've now got everything linked together. We've got our IED simulated. We've drawn a nice one line, but you might still be wondering, how does the behavior actually occur? For example, when a breaker gets a signal, a trip signal, how does it know to try and update its position? Well, what we've done is we've implemented behaviors for different logical nodes in a variety, well, not a variety, really two different languages. One of those would be JavaScript, and the other one would be 61.131. If you don't have a preference between the two, then you really never need to worry about which one it's implemented in, and you don't need to ever touch it. But should you want to modify the implementation we have for the behavior of the different logical nodes, we do make that available. So for example, for the QA0, this is not actually a logical node, this is actually the physical breaker itself. I'll show you what the scripting looks like for that. So I come up here to my breaker simulation. This is just a piece of code that exists every time I have a breaker. So that would apply here for QA0 and bay 1, but also every other bay that includes a breaker. This bit of code will be instanced and executed. So this is structured text, which is one of the languages that is available as part of IEC 61.131. It's probably most widely known and widely used within the control community, specifically on PLCs. So ladder logic would be a cousin of this. We do also include support for function block diagrams, and you could do all of your scripting in function block diagrams, which provides a nice visual representation. So as I mentioned, this logic here just describes the behavior for how a breaker would work. We basically started out by drawing a state machine that describes a breaker, and then we've implemented it here in structured text. Should you be more comfortable with JavaScript, then you would need to come in here. Let's see, so a different breaker or a different element that's been implemented in JavaScript might be XCBR. I could come in here, and if I go to manage edit behavior, that will bring up the JavaScript editor, and you can see how this is the code that we've written for the XCBR in particular. Depending on your comfort, your level of comfort with different programming languages, we find that some prefer JavaScript, some prefer 61.131, and some prefer neither. And the good news is, if you don't prefer either, you really don't have to come in here and ever make changes to these behaviors in either JavaScript or 61.131, because we have created base implementations for you. It's really only something that you would need to come in and tweak. Should you want to maybe, let's say, make your digital cousin a little bit closer to a digital twin. To come back to our car analogy, we could say, we know that our car has a carburetor, and we've implemented a base version for how a carburetor might work. But should your carburetor operate a little bit differently than the one that we've designed and implemented, you do have the ability to come in and make tweaks to make it more similar to how your specific implementation on your specific vendor's IED actually works. So just to recap, before we move on, we've simulated, we've drawn our one line, we've linked our one line over to elements contained within our substation section that exists over here on the left-hand side. In order to animate it, we've linked behaviors to these different components within the substation section that are done in both JavaScript and 61.131, and we've linked our substation section down to specific logical nodes that exist on IEDs down in our IED section. So of course, what this all means is that it can all work together to create a realistic simulation that actually includes real 61.850 communications flying between our devices, just like you would have in an actual substation. So let's take a look at some of this in action. What is it that we've all been building towards? So over here on the right side, you'll see I have a couple different buttons. These are broken up by bay, and these are generated automatically because of one of those selection boxes that I selected when I import imported my SED into DTM. So up here at the top, I have bay 1, I've got my distance protection elements and my overcurrent protection elements. I have 3 different zones for my distance protection, and those are the functionality for those is contained within a PDIS logical node that exists on the bay protection unit over here. It would actually be this particular IED. So when I click that button, what we're going to see happen is that this QA0 is going to open. But what's happening under the hood is that distance protection element is actually sending a start signal or an operate signal over to the PTRC logical node that also exists on the bay protection unit, and that's being passed down, in this case, to actually a second PTRC that exists on the PIU, which is in turn passing that message over to the XCBR, which then tries to operate the breaker. The breaker will in fact open, and we'll see the position value updated over here on my single line. So I'll go ahead and click that button. And sure enough, very, very quickly, we see that that breaker did in fact open. It's a small change, but this little curved line over here on the left did move back. So let's do something a little bit more exciting. You might recall during our last webinar, when I was configuring all of this using Helix, configuring my whole SCD, I also put in some breaker failure functionality. So you might be wondering what these 2 green check marks do next to each breaker. Effectively, the first one disables the trip coil that you might have as part of an actual breaker out in the field. And the second one disables the retrip coil, which would typically be energized by as a secondary effort to retrip if the first one should fail, and might be used by a breaker failure function, for example. Before it issues an operate external, the operate internal that we'll see in just a moment might try and flip that breaker. So now if I issue the same fault again, or simulate the same fault, the zone 1 distance protection in bay 1, what's now going to happen is we're going to see it fails to open because I've disabled those 2 trip coils associated with that breaker. And instead we're going to see the breakers in bay 1 and bay 5, our 2 transformer breakers, they're instead going to open, thereby clearing the bus and protecting us from the fault. So I'll go ahead and click that button again. And sure enough, if we come down here to bay 2, we see QA0 in bay 2 and QA0 in bay 5 have opened, protecting us from the bus. So originally this is where we thought we'd end the demo, but we decided, well, you know, we wanted some opportunity to show you the communications that are happening between these different IEDs. And we already have the perfect tool to do that. And that's going to be Test Suite Pro. As I mentioned earlier, Test Suite Pro is a testing tool that really is specific to 61850. It's full of visualization features, testing features. It has a whole built-in test sequencer that can allow you to do some pretty impressively complex tests. And it really can be used in both a lab setting or in the substation itself, used by either a substation engineer or a technician to test and diagnose and troubleshoot events that might be occurring in your substation. So I don't have time to go through all of those features today, so I'll really just focus on 2. The first of these will be the signal flow diagram, and that's what you see up on the screen here. So these different teal boxes that you see represent different IEDs that I contain within my substation. These names might be familiar. E01 BPU, that's going to be the bay protection unit in bay 1. And then over here on the right, we have E02 PIU and E05 PIUs. So PIU stands for Process Interface Unit, and this is the last device that exists before the physical breaker, the piece of conducting equipment, and it's what will issue the open and close commands to the breakers. So what this whole signal flow is intended to capture is the breaker failure that I just simulated over in DTM. Now, there's not some back-end communication between these 2 tools. Test Suite Pro is simply monitoring Goose messages that come across a wire, as well as MMS reports, which are necessary for messages that are internal to a single device. And I can talk a little bit more about that in just a moment. But let's go ahead and start a capture here in Test Suite Pro. I'll wait just a moment for us to gather the signals, and I'll come back over to DTM once that is completed. All right, and I'm going to disable the trip and retrip coils over here on breaker QA0 and bay 1, and then I'm going to trigger that same protection fault again, and just like we saw before, these 2 breakers in bays 2 and 5 should open. All right, they did. So now let's come back over to Test Suite Pro and take a look at what happened. So it all happened pretty quickly. So I'm going to stop the capture and step through it to give us a little bit better idea of how these signals actually flow. So the first thing as I step through is when I click that button, the distance protection operate.general message picked up. Now, this was documented via source ref that this should be passed into the distance protection PTRC that exists on the BPU or Bay Protection Unit. And that's represented by this box right here, which represents that logical node. Now, very shortly after, that distance protection unit is going to send out a goose message and let the PTRC over in the PIU know that it should tell the XCBR to open and actually update the breaker position. And depending on your familiarity with 62850, you might be surprised that we do have PTRCs in both, but this was a design decision that was made over in Helix because the manufacturer of the PIU typically does use a proxy PTRC. So the opt.general came in, and sure enough, the PTRC did its job and it sent out the trip signal. And that was routed to two different places. One, documented internally by source ref, was over to the XCBR itself over in the Bay 1 PIU. So this XCBR is now going to try and open its breaker. But recall we disabled the trip coils on that breaker, so it will not be able to open. The trip signal is also sent down to the RBRF, or the breaker failure logical node. And the breaker failure logical node, again, this is defined by a source ref and implemented by an XREF. When it receives that message, it's going to begin two different timers. The first timer will be how long it waits for the position to update from the breaker before it sends out an operate internal, which is basically a secondary trip to the XCBR. If we hit next, we see that first timer has expired, and sure enough, the operate internal signal has been sent over to the XCBR. We did also disable the retrip coil on this breaker, so the breaker position still will not update. Next, the second timer in the breaker failure function will update, and it's now time to do its job. It's in the operate external signal, which will be passed over to the two XCBRs in bays 2 and 5, indicating to those breakers or XCBR breaker interfaces that they should in fact update their breakers or open their breakers, which they did. And we can see that reflected over here by the position value updating for those two different breakers in bays 2 and 5. Now, depending on your background and how familiar you are with 61850, you might prefer to see this same information over here in the logic analyzer. It really is the same set of tools. I'm just going to take a peek at a capture that I already have. But basically what we see here is the same thing, but in a different format. This looks a little bit closer to maybe a digital analyzer or oscilloscope that you might have used in a traditional substation. If I turn on my cursors, I can take a look at the timing that occurred between the different signals as the same thing occurred. So the distance protection picked up, and as we saw, almost immediately the PTRC issued an open signal or an operate signal that was received by the PTRC over in the PIU, which then in turn operated its trip signal that was received by the RBRF, the breaker failure logical node on the Bay control unit. And when it didn't see the breaker position update, it went ahead and issued its operate internal a short time later. And then when that still didn't update, then we can tell that the operate external signal was issued out from that same breaker failure logical node. And finally, the position of those two breakers did open, and that would be the breakers in bays 2 and bay 5. So with that, I hope I've explained to you how a simulation such as this is useful, how it can be accomplished really with minimal effort over in DTM, how the import substation wizard can make this whole thing so much easier, especially when you have a well-formed SCD that contains a substation section. And I hope this is something that you guys are willing to try on your own. I will mention some of these features, specifically the 61131 is unique to our DTM 2.0, which is an upcoming release. However, everything else that you saw today, including the JavaScript, is available in the release build of DTM 1.6, which is available on our website. If you are interested in learning more about any of these tools, such as Test Suite Pro, I encourage you to check out some of our webinars that we've done in the past, all of which are available on our YouTube channel. And additionally, send any questions that you might have about future webinars that you'd like to see. And with that, I'm going to go ahead and turn it back over to Beth.
Great, thanks, Jackson. That's actually perfect timing. So we're at the end of the hour right now, but we are happy to stay on longer to go through some questions and answers. What I'd like to do just real quick before we do that is just wrap up some final thoughts. So Jackson, I'm going to go ahead and just take the screen from you for a second. So once you do sign off on the webinar, we do have a survey that we really appreciate if you took a minute or two to answer. It's only a couple of questions. You are also eligible to receive a professional development hour for attending this webinar. So please let us know if you'd like a certificate for that. The recording for the webinar will be posted to our website in about a week. So look for that there if you'd like to see it again. And then if you already have not, please go to our homepage and sign up for our newsletter. That's where you'll be notified of future webinars, training events, any product releases, and just a good way to stay in touch with what Triangle is working on. And as always, if you have any questions or want additional information, please email sales@trianglemicroworks.com. So with that, I'd like to go ahead over to the Q&A session. And I'll just take it kind of from the top. We have a couple of questions. Some of them have already been answered online, but we can share them with the entire audience. So the first question, and Jackson, this might be for you. Based on the existing SCD, how long did it take to configure the test scripts on DTM in order to put this demo together? I'm just trying to get an idea of the amount of time it takes for someone that is already trained in the tool.
Sure, so that's a great question. So the scripts themselves are packaged with DTM and they are already available. So when you download the tool, the scripted behaviors, if you were to download 1.6 from a website today, which is available for a free demo, or free trial, I should say, when you import your SCD, if it has a substation section, it will be created. Or if it doesn't have a substation, you can do it manually. But the scripts themselves are already there and already available. You don't need to come in and manually edit them or make any changes to them if you don't need to. Really, the only reason to is if your particular substation implementation differs greatly or widely from what we have scripted. But from our experience, that is generally not the case. We have tried to create a nice general solution, and most of the logical nodes that are used in a typical substation don't really have that complex behavior. They only become particularly complex when they all work together. The biggest exception to that would be probably some of the protection elements, which are typically unique to vendors. But we're not simulating that level of detail. If you notice in my simulation, I just clicked a button to simulate a distance protection fault. I wasn't actually injecting sampled values. That is an option that you can do, but typically for this level of simulation, we just click a button to simulate a fault. The work that you would have to do in order to bring the simulation up, if you're not using source refs, then you might have to manually make some of the linkages between the L nodes that you saw within my substation section and the different logical nodes that exist on the IEDs that you're simulating. It's not a hard process. I guess it really depends on the time of your substation or the size of your substation. We've done everything we can to go ahead and make those links automatically, but in some cases, say your design uses GGIOs instead of the functions that are defined in the standard or the logical nodes defined in the standard to perform a specific function, you would need to come in and make those manually. That does take a little bit of time, but depending on the size of the substation, maybe an hour or two.
Okay, thanks, Jackson. Next question can go to either Jackson or Christoph. If the SCD file was created, for instance, with IET 600, would it be compatible with this tool?
Okay, I can take that. I think I answered it already in the chat. So basically, the compatibility with the tool, okay, there's the standard compatibility. So if IET 600, which is the system design tool from ABB, for those that are not familiar with it, if IET 600 creates an SCD file that is compliant to the standard, the tool, our DTM, will be able to import that and use it. But then, as it has been mentioned also in some of the other questions and answers, and like Jackson explained before, At the end of the day, it's less about what the tool produces, it's also how you make your design. Most of these tools you can add more or less information when you do a design. So as an example, the xrefs that are the signals from the goose messages going into the L nodes, in the logical nodes of the IDs, they are better there. If they are there, then you can automatically create the link. If not, you need to do it manually. But you still can load the file and do it. So the compatibility is less about the compatibility of a tool. When it's compliant to the standard, it will work. It's more about how much design details do you put in your SCD file, which makes it then easier or less easy to implement the simulation. And that's where the impact comes. How fast can you build such a simulation? So the more complete the SCD file is, the easier it is to simulate it.
Okay, thanks, Christoph. Next question, I believe this one will be for you, Jackson. Do you need an outside tool to create a compatible single line diagram for DTM?
I guess the answer is yes and no. No, you do not need an outside tool. There is a built-in drawing tool that allows you to create whatever you want. And many people who use DTM outside of 61850, build their own one lines for a GNP or 104 substation, or they just build control screens to perform, functions that they're doing outside of simulating a substation. However, if you do want to define the substation section portion of an SCD, which contains conducting equipment and how it's connected and XY coordinates, that would need to be done in a system configuration tool, such as Helix. And then instead of having to draw it yourself in DTM, we could import that.
Okay, next question. I believe this will be for you, Christoph, or maybe Jackson, you guys can decide. I see how you selected inputs for an IED, many of which are points from other IEDs sent over Goose. How is that information stored on a CID level for an IED to parse out specific points from Goose message data sets?
So maybe I can start, and then Christoph, you can fill in the gaps. So the XREFs are contained within the CID. So the XREF will tell you what Goose message a specific IED is configured to receive. Now, depending on the IED manufacturer and depending on the system design, those XREFs might be contained within the, let's say, consuming logical node, the actual logical node that needs that message, or they could be contained somewhere else, like, for example, LLN0. Now, we basically have an algorithm that tries to make those connections automatically, but it's a lot easier if they are placed in the specific logical node that will be using that message. But sometimes two logical nodes will be using the same Goose signal, or for other reasons, they might be placed in LLN0. And that's really where the source refs come in. And that's the problem, or I wouldn't say it's the primary reason that source refs exist, but it's one of the primary benefits from a simulation perspective of source refs. We now know in the substation section which L node was intended to receive that message, and we now know where the XREF lives that implemented that specific connection or input, and therefore we're able to make that connection automatically if the source ref is present and configured. Christoph, could you elaborate?
Yeah, I think I also answered that question in the chat. I think the question was also including a little bit about graphic visualization and how you can do the design. When you have seen the first part of the webinar, Jackson had shown how the things are developed in the Helix tool, where you basically do a graphical way to define the signals that are flowing. Additionally, what we are working on is in visualizing as well an application. So when you have all the source refs, you have all the connections in the SCL file, that's correct, but then the question is about visualizing it. And we are currently working on adding extensions to DTM to visualize as well such interactions. There's an ongoing work in a project with Elia, which is the Belgium TSO. They are doing a proof of concept currently, and within that we are investigating a couple of these things, and we probably will have a future webinar on that later this year or early next year.
Okay, next question. Will measurements be visible in the single line diagram?
So I guess when you say measurements, I'm assuming that refers to things such as voltages and currents. I guess that is an assumption, but yes, that is possible. You could simulate a device which subscribes to sampled values. I will point out from a computational perspective that does it is more difficult to do on a basically a Windows platform. So depending on the number of sampled values that you needed to subscribe to, you could need a more powerful PC. And then of course you do need some way to generate those sample values, which is even more computationally intense. You can do that in DTM, but we typically, we've also seen people use external basically test sets to generate those sample values. But once you have those messages, the single line canvas that I showed, it really is more of a generic HMI tool, or at least visualization tool, and it is just a single line tool. And you do have the ability to bring over basically just like a number element like you would have on a typical HMI, and you could link that to anything, including a sample value measurement or something else, maybe something that's coming in via report periodically instead of multiple times per second, and that value could be updated. Additionally, we do have the power simulation that can provide kind of a basic power flow, and you can set voltages and currents, and you could see those updated on the screen, but that does not resolve all the way down to like a sample value level.
Okay, next question. This one might be for you, Christoph. What about defining the L nodes used in the IED section without having real IEDs?
Okay, so the L nodes are basically created. The L nodes in the substation section are basically created during the specification phase. So when we are using healings and the top-down engineering process, we create functions and associated logical nodes for these functions, and out of that, the L nodes are created in the substation section. So later then, when the design is made based on the specification, the system configuration tool links these existing L nodes that we have to the LN in the IED that is realizing this L node. But the L node is already there from a specification. Assuming we do a top-down specification, if we just do everything together, it's more or less at the same time that the L node will be created and then the LN linked to it. Not sure if that answered the question.
I would just elaborate that if at least you could, I don't know that this would be a common use case, but you could in DTM just open a blank project, create a substation section, begin to create, voltage levels and different bays and different pieces of conducting equipment within those bays and different L nodes within those, all within DTM. It's not going to generate an XML. It's not going to create any SCL. But if you just were curious, and you wanted to create basically the equivalent of a substation section here within DTM, now you're not going to have IEDs. You couldn't link up signals between different logical nodes as if they were goose messages, but you could link almost like everything was an internal signal directly from one L node that exists on, to another just directly. Now that's not going to be visible, with something like Wireshark. That would all just be internal communications, but you could build a simulation that way with kind of a simulated substation section. Okay.
The questions are wrapping up. I do have one here that I want to end with that I can answer. So the question is, how does one go through the initial ramp up? These webinars are super exciting, but trying to do that myself with the software for the first time means I have tons of questions and it slows down the process incredibly. So a couple of ways that we can help with that. When you do purchase a license from us, we do offer a 1-hour training free session that can be with you or your entire team to get you familiar with the tool so you can get started as quickly as possible. DTM itself does come with a number of sample workspaces that helps you get more familiar with the tool very quickly. You also would have access to technical support that can help you with any questions that you have while using the tool. And lastly, we do offer consulting. We can build workspaces for you and help you with your projects through consulting hours. So there really is a number of different ways to help you get ramped up on the tool as quick as possible, using it to the full extent. So with that, I do see a couple of other additional questions coming in. We will, in our follow-ups, if you answer the survey, we do send the question and answers in a spreadsheet along with the follow-up to that. So you can get a full list of all the answers that were provided today. On that note, I'd like to thank everyone for their time today and hope to see you at the next webinar. Thanks, everyone.
Yeah.